Now I want to briefly go through some stuff with the curl. It's a little different. There is, of course, the magnetic field example. Because in this case, instead of charges, it turns out with the magnetic field, where J is the current or current density, it's the curl equation that you tend to use as the sources. Because unlike the electric field, the magnetic field, there is no source of magnetism in terms of point charges, and del dot B is always 0. So the integral of B dot dA is not a useful thing to use. But since the curl is given by the current, then the integral of B dot dr around some curve is the same thing as the integral over the area of 4 pi j over c dot n hat ds. And again, where is this most useful? This is most useful when you're trying to find B and you have some symmetry. So the type of places we use it, obviously, the most common being a straight wire. What's the symmetry we're looking for here? We know basically what? The magnetic field lines have to be circles in this case. Again, there's no other direction they can really have. And once the magnetic field is known to be a circle, that's the circle we're going to integrate around, and that's the area we're going to look for current cutting through. So the integral on this side is going to have the j dot nds. For a infinitely thin wire, right, that's just a delta function again. And that's why we often see this as the integral of B dot dr equals 4 pi over c, the current enclosed. Because J is the current density, you integrate that over the area, and you get the current enclosed. Little trickier if I have a coil of current. Now, what direction do I want to draw my surface? Well, typically, we draw it down the axis of the coil, because if I turn this sideways, then what do I see? If this is this piece of my current, not my current, of my line that I'm drawing, then the current is coming through it like that. And n hat is parallel to j, which makes my integral over the surface of j dot n hat ds easy to do. So again, let's think about the geometry. My curve is that rectangle, so my surface is now parallel to the plane of the paper. Because I have a coil piercing it, my current is always either coming out or going in to that plane perpendicular to the surface of the plane, which is parallel to the normal. So when I turn it sideways, here's the edge of my rectangle, and here's my coil coming up and through. And as my coil pierces through here, in that one point, it is parallel to n hat. As soon as I curve down, it's not, but I don't care about that because my surface is here. And so the challenge in all of these is getting your 3D spatial ability up to par. You're really looking at, when I'm doing these vector integral things, particularly in E&M applications, I'm looking for symmetries. I'm looking for ways that my integrals can be easy to do and make sense. In this case, once I put all the coils together, the symmetry I'm exploiting is that the magnetic field, which used to be circles, is going to become some sort of straight line. And again, this trick only really works if I then take the limit as this thing gets infinitely long, because otherwise I have to worry about weird shape of my magnetic field at the edges, and I actually have to worry about magnetic field outside. If you do this, you see in the classic textbook case, you can assume the magnetic field outside is 0 because it's been infinitely long and it cancels. So there's a lot of tricks to using these integrals in these fashions. Now, any questions on the magnetic field example of this? And again, it's worth it since we've done all these in this compacted space, to go back and really think about and realize why we tend to use curl for magnetic field, because that's what has the sources is the current. Why we use divergence for electric field, because there you have the 4 pi rho. The divergence of E is not 0 everywhere. Those are the kind of the physics that's underlying things. The other thing that's underlying stuff with curl is in fluid flows or other flow type situations. Often we think of it, because we call it the circulation, as when stuff is rotating. Now, one way to imagine that is put a little turbine or spinner in a fluid and ask, does this spin? So we can imagine uniform flow. So what would that look like? If I pick an x and y axis, this is a velocity field that only has an x component, and that x component is a constant, v sub x. Does this velocity field have a curl? If I take the curl of that, do I get 0 or do I get a non-zero value? Hopefully you can take the curl of a constant in your head. 0, because the derivative of a constant is 0. And if I look at this, would I expect such a fluid flow to spin this turbine? No, because the equal amounts hit the top and bottom. The torques cancel, right? The water hitting here tries to make it go that way. The water on the top tries to make it go the other way. It doesn't spin. So this is a field with a curl of 0. Notice, that tells you something interesting. All those times which we do, when the magnetic field is a constant, which is a common situation to use, right, is a constant magnetic field, that's a very special case. Right? That's when the curl of B is 0. It tells you something about the current distribution. Right? Because we just learned that the curl of B being 0 is related to the type of current that's being enclosed. So you have to manufacture a special current distribution to get a constant B field that has a 0 curl. So this is really telling you, if you're going to be involved in a lot of electromagnetism work, there are very useful ways to think about designing your system. If you want magnetic electric fields with special structures, once you know the E and B you want, then it's easy to take the curl and divergence of it. And by taking the curl and divergence of it, it's telling you something about the currents and charges, where you need to place them. And is this going to be hard? Is it going to be easy? That sort of thing. So it's a very useful way to think about stuff. Now, let me ask you this. So imagine you have what's often called linear shear. So this is a flow that looks like that, where now the velocity is given by some constant times y, but in the I-hat direction. Right? So it's getting linearly bigger as I go up in y, but it's flowing in the x direction. Does this vector field have a non-zero curl? Yes. Why? First, it's clearly going to spin something, which I just told you is what the curl is physically, right? The torque down here is less than the torque up there. But also, if I just take the derivatives, what derivatives show up in the curl? And this is a very important thing to keep in mind. There's an important intuition between divergence and curl that you want to have in mind. In the divergence, what derivatives show up?
The x component with the x.
Right, the derivative matches the component. Yeah. With the curl, what are the only derivatives that show up?
The different components.
Cross derivatives. So here I'm going to take the derivative of the x at some point with respect to y, and I won't get 0. And in fact, that's the only derivative that survives. So since there's nothing to cancel it, the curl has to be non-zero. And now kind of the cool thing is, so let's look at it. We have ijk, we have dx, dy, dz, and we have v naught y 0, 0. And so the curl is going to come out as k hat times the negative dy v naught y. So I'm going to get a negative k hat v naught. So my curl is into the board. Which way does my rotor spin in this case? Into the board, right? If I use my right-hand rule, the top's going to spin more, my thumb goes into the board. So the curl really is related to the rotation direction of this object in the fluid. So that really is a deep physics connection there. Any questions on that? So just real quickly, I think it's important to review the various different lectures that came out. We have this fundamental idea that relates the integrals on the inside and outside. But in this simple idea was contained a ton of physics ideas. There was the flux idea. There was the curl being related to rotation. There was the use of symmetry. There was the different question of whether you're given F or you're finding F. And probably even more that I'm not thinking of right now. So as you go back over these examples, as you go back over the derivations, as you go back over the basic ideas, by combining a whole bunch of these integral theorems into one big concept, there's a ton of physics and math compacted into the last 2 weeks. So it's an incredibly powerful set of ideas, and I really encourage you to look at it carefully. You know, if nothing else, it's a simple trick for integrating at various times.